Hi everyone. So I know you've got a lot of handouts today, so find this one. It's on analyzing normals to predict outcomes of the interactions of three planes in space. So this is kind of going to be your go-to sheet for when you're analyzing normals to predict the outcome. All right, so we're looking at all the different ways three planes in space can interact. So one of the options is that the three planes could all be parallel and distinct. Okay, and another one is two of the planes could be the same and the other one's parallel. And then another one is that all three planes are the same plane and you have a plane of intersection. And these all occur when the three normals are parallel. So when n1 equals some scalar multiple of n2 equals a different scalar multiple of n3. So when the normals are all scalar multiples of each other, or the three normals are parallel, you have one of these three outcomes. And then you would, of course, test the d values to see which one you have. If none of the d values are in the same scalar multiples as the normals, then you would have all three planes are parallel and distinct and no intersection. So once you've determined and analyzed that, you can just say there's no intersection of the three planes. In the second case here, you would find out that for two of the planes, the d values were in the same scalar multiples as they were for the normal, and the third one wasn't. Again, there's no intersection of all three planes. Two planes are coincident, but we're just looking at intersection of all three planes in space. So the only one where all parallels are normal that causes an intersection is if d1 is equal to the same scalar multiple as the normals for the three d values. Okay, so when the d values are all in the same proportions as the normals are, then you'll get a plane of intersection. So I'm going to highlight every time we get intersection. And this time it's a plane of intersection or a pi-OI. So the first kind of box in our chart is when all three normals are parallel. So our columns are how the normals are related, the geometric arrangements that are possible from that, and the intersection if it exists or no intersection. So when we looked at all three normals being parallel, the only time we got an intersection was a plane of intersection when all the d values were in the same scalar multiples as the normals. So now the second thing we're going to look at is what happens if two out of the three normals are parallel. Well, in this case, if two normals are parallel and the two d values are also in the same scalar multiple, then you'll get two planes that equal each other. So say like it could be like pi1 equals pi3. And then in this case, it would be like pi2 would intersect, and they would intersect along this line of intersection here. Okay? And we know how to find that line of intersection two ways. One way is using matrix, and the other way is using the cross product to find the direction, and then using elimination and finding a shared point along that line of intersection. So this gives us a line of intersection. The other possibility is that the normals, two normals are parallel, but the d values are not in the same scalar multiples as the normals, so that, say this is pi1 and pi3 are parallel and distinct, and pi2 crosses through them. And you can see there's like two lines of intersection, but there's no intersection of all three planes at once. There's no spot here where all three planes are intersecting, and that's what we're concerned with. So this also leads to no intersection. So far we've looked at 5 different arrangements, and only 2 of them have given us a solution or an intersection, okay, of all three planes. Now we have, our next one is the normals being coplanar. Okay, so, and we know that our test for normals being coplanar is n1 dot n2 cross n3 is equal to 0. And if you remember why that is, so say we have 3 vectors here. Say these vectors are n1, n2, and n3. I can do the cross product of n2 and n1, and I get this orange vector here, which is perpendicular to both the green one and the blue one. My orange one's sticking up here. And then if I go and dot it, the cross product of this, which this vector is the cross product of blue and green, if I dot it with the pink one and get 0, then the pink one and the orange one are also perpendicular, which means all 3 lie in the same plane. So if the normals lie in the same plane, or coplanar, there's 2 different formations that can occur. So I'm going to show you this one first, which does result in a line of intersection right down the middle here. And I made a model, so look at it and see if you can figure out what I mean by normals being coplanar and my line of intersection. So here's my model. Okay, so here's my 3 planes are pink, green, and blue, and the little toothpicks represent the normals. And you can see that the shadows of the normals all lie on the whiteboard that's underneath there. So meaning the normals are all coplanar, they're all on the same plane. And in this case, there's a line of intersection. I'll put my pencil up here, sorry, to represent the line of intersection where all 3 planes intersect along that line. Okay, so in this case, we have normals, we have normals being coplanar. So all our normals are coplanar, and we have a line of intersection that we can go and find using the matrix. So one possibility, if the normals are coplanar, is that we have a line of intersection, and we would use the matrix to go and find it. The other possibility for normals being coplanar is this possibility here. So again, I have 3 planes, a fluorescent green, a dark green, and a blue one, and I've put the toothpicks representing the normals, and you can see that the normals are all, their shadows are all on the whiteboard, so the normals are coplanar. But in this case, there's no intersection of all 3 planes. There's an intersection of 2 here, 2 here, and 2 here, but none of all 3 of them. So this leads to no intersection as well. And the only way to tell between these 2 is the matrix will tell us. Okay, so the matrix will tell us which one we have. So when the normals are coplanar, you're going to go into the matrix, and the matrix will either tell you they have a line of intersection, or it will tell you you have no intersection, and you'll be able to decide between these 2 geometric arrangements. And then the last category is that the normals are not coplanar. Okay, so if you do n1 dot n2 cross n3 and you don't get 0, then you automatically have a point of intersection, and you could go into the matrix and find that point of intersection. So again, first thing you're going to check for are any normals parallel. If all 3 normals are parallel, you're going to pick between these 3 by looking at the d values. Only one gives us intersection of all 3 planes. If 2 of the normals are parallel, you're going to decide, are the 2 normals that are parallel, are their d values also in the same scalar multiples, meaning that the 2 planes are the same, and then they'll intersect with the 3rd one for a line of intersection? Or are the 2 planes that have parallel normals parallel and distinct, which would result in no intersection? Then if we have no normals that are parallel, then we test to see if they're coplanar. So if n1 dot n2 cross n3 is 0, we would go into the matrix and decide between the line of intersection or no intersection, depending on how our matrix works out. And then if the normals are not coplanar, so if we didn't get 0 up here, we know we automatically have a point of intersection, and we would use a matrix to find that point of intersection. Okay, so before we get into matrices, we're going to try just doing our normal analysis here. Okay, so you want to find this sheet next. Normal analysis should be two-sided. We're looking at the intersection of three planes, and all we're going to do here is analyze the normals to predict the ways three planes will interact in space. By using normals, we're going to analyze the geometric relationships of the three planes, and then we're going to use this sheet and figure out which picture our normal analysis leads us to. And I'm going to tape it on here, cut it out and tape it on here to show the geometric relationship. And if there's more than one possibility based on our analysis, we'll just cut out two pictures. And for now, that's what we're focusing on. We'll learn how to actually go through and find them in the next lesson. All right, so here's A. So the first thing I would always do is find out what my three normals are. So 3, -3, -2, 5, 1, -6, and 1, -2, 4. So I look at those and I don't see any scalar multiples there. So I know that I don't have three normals being parallel or two normals being parallel. So now I'm going to go and see whether or not they are coplanar or not. So I'm going to do N1 dot N2 cross N3. Okay, so N1 is 3, -3, -2, and I'm going to dot that with the cross product of these two. So +4 minus 12 is -8. -6 minus 20 is -26. And -10 minus 1 is -11. And then we're going to do the dot product. So that's going to give me -24. Get my calculator. -3 times 26 is -78. And then plus 22. It's -80. So they're not coplanar, which means that you have a point of intersection in this arrangement. I forgot to show you, so that would mean therefore there's a point of intersection. But I made a model for that I forgot to show you earlier, so I'm going to show it to you now. So this is my model with the normals in, so you can see here. So here's my three planes. And one of them's the yellow color that you see. One of them's green here, and one of them's blue. And you can see that here's my two normals you can see, but this is also a normal here. See it? And you can see that they're not coplanar. I can see that these two are coplanar, or if I turn it a different way, I could have two more that are coplanar, but always one's going to be not coplanar to the other two, okay? And then if you can see, the only place where these three planes intersect is right in that point there, where the blue one, the yellow one, and the green one, just that one point, and that's why there's a point of intersection, okay? Where the normals are not coplanar. So you see the two normals here, and all you see is a dot because that one's not coplanar, okay? And again, the point of intersection is right there where my pencil tip is, where the three planes intersect. So that's the case for this one, because when we analyze the normals, that's what we got. So I'm going to look at my sheet here and cut this one out, this arrangement out. And tape it on. I've got some tape right here. And So that's the geometric arrangement. That's what it will look like. So we have these two planes and then the third one, and then our point of intersection is going to be right where the three planes meet. And we'll learn how to find that in our next lesson. All right, for B, again, we're just going to start off by looking at what our three normals are. So if I'm looking at my three normals, I'm seeing that normal 2 is 3 times normal 1. So those two planes are scalar multiples of each other. And now I'm going to check, is D2 equal to 3D1? So they're both on the same side, so I can compare them. Is D2 3 times D1? Yes, this is true. So that means pi 1 equals pi 2. And pi 3 is going to intersect them in a line of intersection. So if we look back at our sheet here, we've got two normals that are parallel, but their d values are also in the same proportion, so those two planes are the same. In our case, it was plane 1 and plane 2 that were the same, and the third one's going to cross through them, and we're going to get this line of intersection. So the picture that we want to show is this picture right here. So I'm going to cut it out. And tape it on. I'll tape it on here. And again, that line of intersection is going to be right along here. Okay? And we can use matrices to find it. We learned that on Friday. But right now we're just analyzing the normals to predict the outcome. Okay, for C, we're going to look at our three normals again. So N1 is 3, -1, -2. N2 is 1, -1, 1. And 3 is 1, 1, -4. And if I look at those, none of them look like scalar multiples. So now I'm going to check to see if they're coplanar. So I'm going to do N1 dot N2 cross N3, which is going to be 3, -1, -2 dotted with, and then I'm going to do the cross product of these two. So 4 minus 1 is 3. 1 minus -4 is 5. And 1 minus -1 is 2. So I'm going to dot product. So 9 minus 5 minus 4 is 0. So the normals are coplanar, which means if we look back at our chart, there's two possibilities for normals being coplanar. Either you can have the line of intersection, kind of like this star pattern, or you can have kind of like this triangular pattern, which leads to no intersection. And we haven't learned yet how to tell the difference, but we will in the next lesson. So for now, we can only narrow it down to two possibilities. So it's either going to be a line of intersection, which is this one. Therefore, either LOI, which is this one, or no intersection of all three planes, which is this picture, the triangular looking one. Okay, and the last one that we're going to look at to analyze the normals. N1 is 1, negative 2, 3. N2 is 1, 1, negative 1. And N3 is 2, negative 4, 6. So I'm looking at these and I can see that N3 is equal to 2N1. So now I'm going to test, is D3 equal to 2D1? So D3 is negative 5, and D1 is negative 9, and D3 is not equal to 2D1, so this is not true. Okay, so that means pi 3 and pi 1 are parallel and distinct. Since they never touch each other, all three of them can't touch each other, because automatically those two never touch each other. So that's going to be this arrangement here, where we have two planes that are parallel and distinct, and the other one cuts through them. But again, that's no intersection of all three planes. So therefore, no intersection. So if we look back at the 4 that we've analyzed the normals for, the first one we got a point of intersection that we would have to use the matrix to find. And the second one we got a line of intersection, which we would use the matrix to find. The third one we got between 2, we got either a line of intersection or no intersection that we would have to use the matrix to find. And then for the fourth one, we got no intersection and we wouldn't need to go any further than the normal analysis. So the normal analysis is really important so that we know what we're expecting to get. And that can help us because, as we've seen before, you can make many mistakes in the matrix easily with all the numbers, and you want to be able to get what your prediction is. Also, like, double check your cross products and stuff when you're doing your normal analysis, because if you make a mistake there, it could throw you off as well. All right, so in our next lesson, we're going to learn how to use matrices to actually find points of intersection or lines of intersection.